Now, you've seen those breathtaking images from NASA: stars born in clouds of gas, tangled galaxies, colors that look fantastic and vivid. And then someone suddenly says that this isn't real, that NASA edits all these pictures. Well, guess what? They're right! NASA does edit their photos, every single one. The catch is that it's not to deceive us, but rather to reveal what we could never see on our own. You see, color is a weird thing. It's just waves of light and energy flying through space. When these waves hit some object, a banana, a chair, or even a dust particle, the objects absorb some of the waves, eating a part of the spectrum. But some of it bounces back into our eyes. That bounced light is what we perceive as the object's color. There's an entire spectrum of these waves, from short ones to long ones. As they get longer, they move to the red spectrum and turn into infrared, microwaves, and radio waves. As they get shorter, they move closer to blue and violet, turning into ultraviolet, X-rays, and gamma rays. Now, right in the middle of that spectrum is a tiny band we call visible light, which is the only part our eyes can see. That's the rainbow we all know and love, and it's an exceedingly small part. So, you might say we barely see the world at all. When light bounces off something and gets into our eyes, our color-detecting cells, called cones, send them to our brain. So when we say, "banana is yellow," it means banana ate red, green, and blue waves and reflected yellow waves into our eyes. So the question is space actually that pretty and colorful, or is it all fake? Well, yes and no. Stars emit light, and it travels through space like an unstoppable train. It's flying there, chilling, until it hits something – dust particles, a planet, spaceship, or an astronaut. Every time light hits something, some of it gets absorbed, some of it reflects and continues to travel. So we get less and less light every time it hits something. And when you enter a nebula, which is basically tons of dust particles around a gas cloud, light quickly starts to scatter and disappear. Nebulae, which is the plural of nebula, also grow naturally from ionized gases like hydrogen, oxygen, sulfur, radiating light in specific spectral lines. But it's super faint as well. Remember, our eyes see things only when light bounces off those things in our eyes. On top of that, the color-detecting cones in our eyes aren't so great, in that they need lots of light to activate. We can't see faint stuff. Unless there's something emitting light right there nearby, we wouldn't see anything. In other words, for us, the entire space would be like a room with lights turned off. The potentially beautiful nebulas and planets are there, but if you don't have a lamp nearby, you can't see them in all their glory. When there's lots of light around, rods take over, another type of cell that's great for motion and dark vision, but terrible for color. So in deep space, all we'd see are dim whites and grays. Now, if you were flying around on a spaceship, the stars would look sharp, white, and non-twinkling. You'd be able to see some reddish or bluish tints to the brighter ones, like Betelgeuse or Rigel. But a lot of things would be dim gray smudges at best. The Milky Way might appear as a cloudy band, not rainbowy like in astrophotography. Nebulae would look like faint fuzzy clouds with no color, unless it's something that glows very brightly, like the Orion Nebula. In our solar system, astronauts can see stuff thanks to the sun or when they're near illuminated planets or spacecraft. Planets like Jupiter and Mars retain some color for our eyes. Meanwhile, on Earth, the sky would look black during the day if we had no atmosphere. The sun would be a bright disk in a void as seen from the moon. If only we had super-sensitive cone cells that could detect light better than we do and see even faint things. Oh wait, we actually do have technology for that. Long-exposure cameras and telescopes. Now, telescopes are great for that. They often use long exposures to gather light over minutes or entire hours. That lets them capture photons we'd never collect with our eyes. When telescopes like Hubble or the James Webb take photos, they're not snapping pretty pics like those on Instagram. They're collecting all this raw, invisible data, numbers and faint light that's both within and beyond human vision. The James Webb Space Telescope doesn't even see visible light. It's built to detect infrared or heat. Telescopes like that work like time machines. They show not only distant galaxies, but also what those galaxies looked like billions of years ago. We see stars that have long since gone out, and galaxies that may have already disappeared. All because the James Webb can pierce through gas and dust and see galaxies so old that their light has been stretched into infrared wavelengths as the universe expands. In other words, this telescope isn't made to let us take aesthetic photos. Its main goal is to study the history of the universe. Now, at first, this stuff looks like grayscale or even black images. When the James Webb sends data back, it looks empty. But during post-processing, astronomers map wavelengths they received to visible colors. Every color in those pictures is chosen for a reason. It highlights specific wavelengths, gases, or temperatures. In any case, it shows what would otherwise be completely hidden from our eyes. Sometimes they show only stuff a human eye can see. Sometimes they shift colors or add something to show elements or intensities. For example, let's say you're studying a supernova, a star blowing itself to pieces. You need to see its debris clearly to understand what's going on. That means you'd play with the contrast or adjust color balance to reveal specific gases and find pale objects near bright ones. Want to check out a weird rock on Mars? You zoom in, adjust the lighting, boost the shadows. Photographers do this every day. So scientists do it too, because clarity means understanding. Even old photos from the Apollo missions have been touched up in modern times. It's like restoring an old film so it looks crystal clear instead of foggy. Without this editing, the most incredible discoveries of the past 2 years, those first galaxies, those newborn stars inside cosmic clouds, would just look static. Is it possible to accidentally misinterpret the color? Of course! For example, images we get of Mars are mostly red, but when we land on the planet, it's more colorful. Most of it is gold, yellowish, tan, or brown. The reason Mars looks reddish is due to rusting iron in the rocks, Martian soil, and dust. It all depends on the lighting, atmospheric dust, and image processing methods. But the fantastic colors themselves are not made up. Galaxies contain billions of stars, gas, and dust, giving off incredibly rich color ranges. NASA's photos are basically translations. Now here's an interesting take. Could we use goggles with night vision or some technology that makes our eyes notice light better, like working with Hubble or the James Webb? Man, the sky would be insane. You'd never be able to sleep again. These magical astronomy glasses should greatly amplify faint light, enhancing and translating colors. Unfortunately, today's night vision tech won't cut it. Night vision goggles work by amplifying visible and near-infrared light, but they display everything in green monochrome, not true color. Meanwhile, infrared goggles detect heat, not color. We need some goggles that raise photon sensitivities by 10,000 or so. If only we were lucky enough, like some animals. For example, snakes can see infrared, bees see ultraviolet light, and birds see more colors than we do. And we can't even imagine how they perceive the world. So yeah, NASA edits their photos, because raw space isn't built for our eyes. It's dark, cold, distant, and silent. But with a little translation, some math, some color grading, some visual storytelling, we can see the invisible. We can study the past and inspire more people to study space in the future.
So get this. Earth might be actually located near space highways that could connect us to other worlds. That's because our sun sits right in the center of a giant bubble filled with hot gas, carved out by ancient supernovae. And this bubble likely has tunnels linking us to distant galaxies. So, does it mean it's time to develop space tourism? Well, let's figure it out. Most of us think space is just planets floating around in eternal darkness. But new research hints at the possibility that it might not be really true. It turns out our whole solar system is actually sitting inside a giant bubble of hot, thin gas. And it gets even better. Scientists now think there might even be a weird cosmic tunnel or channel made of this stuff. It supposedly stretches out toward faraway stars. Astronomers spent years mapping the sky, and after they put all the data together, they found something that looks like a long pathway of hot, low-density plasma, which is basically that very thin, superhot gas. And this so-called channel reaches out from around us to distant constellations. Researchers from Germany confirmed this discovery using data from a space telescope called eRosetta. We'll talk about it a tiny bit later. Now, interestingly, scientists discovered that our solar system sits inside something called the local hot bubble a long time ago. This bubble is actually a huge area, about 1,000 light-years wide. It was created when several stars exploded in giant supernovas millions of years ago. Those explosions heated up the gas around them and basically carved out this bubble of hot, low-density space. And their shock waves created weak points in the bubble around us, eventually forming interstellar tunnels. That cosmic event was so huge that the leftover hot plasma is still floating around us today. Now, to understand this bubble better, scientists used eRosetta, which is an X-ray telescope. It scans the sky looking for soft X-ray light. That's a kind of light we can't see with our eyes. It comes from hot gas, old supernova leftovers, and other structures in space. They also compared eRosetta's new information with older data from another X-ray telescope called ROSAT. And finally, putting all this information together, they were able to make a much clearer map of what's around our solar system. Mind you, this wasn't easy. They had to divide the sky into thousands of tiny pieces and carefully measure faint signals coming from warm gas, empty pockets of dust, and other stuff floating in space. But their effort paid off. After sorting through everything, they managed to figure out the faint glow of hot plasma around us. It proved we were not just drifting through empty space. We're inside a giant burned-out bubble created by extinguished stars. But what really surprised scientists was the discovery of some kind of channel. It looked like a long tunnel in space, cutting through the hot gas around us and connecting our part of the galaxy to star systems far away. They also found signs of another channel pointing toward the Canis Major constellation. And those might not be the only ones. The data suggests there could be a whole network of such paths, branching out through space. Each one works like a hidden back road. Scientists used to guess that the space around our solar system might have little pockets or rooms carved out by old exploding stars. We could probably imagine them like caves inside outer space, but no one had the necessary tools to actually prove it. But now, thanks to that new data from the eRosetta telescope, they finally have a clear picture. The telescope showed that the space around us wasn't just empty. It's full of hot, thin gas and strange shapes, including tunnels and bubbles. This proves at least part of what older scientists predicted. We're living inside a giant bubble of hot gas, and that bubble connects to other bubbles through long, low-density channels. The new study also shows that the pressure inside our bubble is lower than scientists expected. This might mean the bubble isn't closed. It could be open in some directions, letting that hot gas flow out into other parts of space. In short, this hot bubble isn't simple at all. Parts of it might be open pathways, and other parts look blocked off. Being inside it is kind of like trying to walk through a forest. Some areas have clear trails, and others are packed with trees. And even though astronomers have mapped big chunks of the bubble and found these strange channels, there's still a lot they don't fully get. Some paths look like they're made of a bunch of connected empty pockets, and others look totally closed. To understand the whole picture, we'll need better tools and more data. Hopefully, with stronger X-ray telescopes, deeper sky scans, and better computer models, we'll finally understand the nature and structure of the bubble we're living in. we might be able to make a kind of map of those hidden channels and learn how they affect things like cosmic rays, dust, and the solar wind around us. Now, speaking of telescopes, we can't help but mention the one that helped us figure out the very existence of the bubble around us. The thing is, scientists have been trying to understand a faint glow of low-energy X-rays that seem to cover the whole sky. For many years, they weren't sure where this glow was coming from. And then, the NASA-supported DXL mission finally helped to solve the mystery. Researchers used old but reliable detectors that first flew on a rocket in the 1970s. With these instruments, they confirmed that most of this X-ray glow came from a huge area of extremely hot gas around us. It was named the local hot bubble. Back in the 1990s, another X-ray mission called ROSAT made pretty good maps of the sky, and it found something surprising. Comets gave off soft X-rays too. Later, scientists realized this happened when the solar wind, fast particles from the sun, collided with neutral atoms. This process, called charge exchange, can happen almost anywhere in space. Because of this, some scientists started to doubt whether the local hot bubble was really the main source of the X-ray glow. So, to test this, DXL launched on December 12, 2012 from New Mexico. The rocket flew high above Earth's atmosphere for about 5 minutes, giving the instruments a clear view of space. The goal was to look at a worst-case situation where lots of charge exchange might occur. Right now, our solar system is moving through a cloud of cold gas in space, known as the local interstellar cloud. That's also nicknamed the local fluff. Cute, right? Neutral hydrogen and helium atoms from this cloud move through our solar system at very high speeds. Hydrogen gets affected easily by different forces, but helium mostly follows the pull of the sun's gravity. Because of this, the helium forms a focusing cone, a region with extra helium that Earth passes through every December. This cone is the perfect place to look for charge exchange, since it holds more neutral atoms than usual. But what happens during charge exchange? The solar wind comes from the sun's corona, the star's superhot outer layer. The particles in the solar wind have lost many of their electrons. When one of these particles hits a neutral atom, it can steal one of the atom's electrons. The stolen electron briefly gives off a soft X-ray. This is how the glow is created. Now, to compare things, the researchers also looked at old ROSAT data from 1990, taken in a direction away from the helium cone, where charge exchange should be weak. By putting everything together, the scientists found that only about 40% of the soft X-rays come from inside our solar system. The rest, the majority, comes from the local hot bubble. This means the huge cloud of hot gas around us really is the main source of the X-ray glow. But let's get back to the discovery of the Space Intergalactic Tunnel. It's a valuable lesson for us that space might look calm and empty when we look up, but that's not true. Space around us actually contains dust, plasma, radiation, magnetic fields, and mysterious tunnels. All of these things mix and swirl together, making space much more complicated than a simple vacuum.
Dozens of spacecraft and hundreds of probes take off from Earth and head for our planet's twin sister, Venus. It's about the same size as the Earth and has around 80% of our planet's mass. The temperatures here are too high for humans, and it doesn't have the air we're used to breathing. But we went there because scientists recently found traces of phosphine gas, which suggests that life might be there. Phosphine comes from various microbes and bacteria, so humanity goes on this journey to discover this life. With our technology, a flight to Venus would take 3.5 to 6.5 months, but we finally made it. Spaceships are landing on the planet, and when the first humans come to the surface, they see heat-scorched deserts, lava lakes, and geysers of poisonous acid. And that's it. Scientists miscalculated the radio telescope data. Phosphine never existed on Venus. So we're going back to the rockets, and we're getting ready for a longer trip across our galaxy. The scientists believe that there's at least 36 civilizations in the Milky Way that are similar to ours. They could be living organisms completely different from us. They may have different bodies, different eyes. They may walk and talk in a very different way than we do. But an advanced civilization has several criteria: technological progress and the use of developed communication between individuals. So, these civilizations must explore space, build cities, and be able to communicate with each other as independent species. Let's look at our galaxy and find these civilized worlds. So, the Milky Way is a spiral of 100,000 light years from side to side. If a star is born at one end of it in a super powerful blast, the light from that event won't even reach the other end until 100,000 years later. There's about 100 billion stars, and near each of them, there may be worlds similar to our solar system. Let's try to find these habitable worlds using giant sieves. First, we look for stars that have a lot of iron. Such stars burn at the perfect temperature for the development of life. And the iron in the star system will help form the cores of planets that will be home to another civilization. We sift the Milky Way through our sieve. We see that there are too many stars that fit the description, so we need another filter. Now let's find stars that look like the Sun in this pile. The star must be about 100 times larger than the Earth and 333,000 times heavier. An important criterion is the age of the star. When a star gets old, it begins to expand and turns into a red giant. At this time, it can absorb the planets around it. The life of such a star can end with a huge blast that destroys everything around it. So the star we're looking for must be relatively young. Let's use our sieve again. There's fewer stars, but still that's a lot. Now let's focus on the planets. They should be in the habitable zone of the star. Not too close to a star because then the temperature would be too high for life to be born. And not too far away. Then the planet would just be an ice block with nothing living on it. The temperature of the planet must allow the water to remain liquid. Another filter is the age of the candidate planet. It takes time for an advanced civilization to develop. Based on the experience of Earth, scientists believe that it takes at least 4.5 billion years for any life form to evolve to the human level. So we're looking for planets similar to Earth or older. We use our sieve one last time, and voila! We have 36 worlds where an advanced civilization is possible. Scientists conducted this study and published it in April 2020, based on these very criteria. All that's left is to discover these civilizations and make the first contact. We can detect such a civilization by using radio waves that come from it. Suppose there's a planet A with primitive living organisms on it. Millions of years of evolution, and they'll become a civilization with advanced technology. Radio waves will be the way they communicate. Then the whole planet will emit radio waves like a star emits light. And here on Earth, we'll be able to pick up this signal with antennas pointed into space. But there's a problem with the distance between the planets. For example, planet A is 1,000 light years away from the Earth. When planet A starts emitting radio waves, these signals won't reach us until 10 centuries later. We learned to emit and receive radio waves in 1895. And if the civilization on planet A emitted a radio signal at the same time, we won't be able to pick up that signal until 2895. It'll be the same on planet A. We sent a message in the form of a radio signal into space in 1974. In this signal, we encoded our number system, human DNA, and information about our solar system. If there's an advanced civilization on planet A, they'll be able to receive this signal only in 2974. And we'd have to wait another millennium to get a response from them. Another problem with radio waves is that they don't look like a constant glow on the planet, but like a flare. Radio waves are only used at a certain stage of civilization. At first, it's the primary method of communication, but then we begin to use cell phones, cable TV, and fiber optics. And as technology advances further, our radio wave light begins to fade out. So we only have about 100 years of active radio use by civilization to find it. One day we caught a strange radio signal of an unknown origin. Its characteristics suggested that the signal was created artificially, perhaps by an outer space civilization or a passing starship. Further searches for this signal given no results, and this gave rise to many theories and arguments as to what it really was. It could have been a signal from Earth that reflected off a satellite flying through the sky, or it could have been the traces of a comet a few light years away. But let's assume it was a civilization from outer space, one of those 36 that probably exist. Now we need to make contact with them. So we throw our luggage into a rocket and head out in the direction of our suspected planet. Our rockets can fly at 17,600 miles per hour. That means a rocket could cross the entire United States in just 8 minutes. But even if an advanced civilization lived near our closest star, Proxima Centauri, it would take us about 73,000 years to get there. Even at the speed of light, it would take 4.2 years, so we need to solve the problem of space travel. Our scientists plan to reach about a quarter of the speed of light with a laser. A powerful laser beam from Earth will push a microscopic probe in the right direction. This probe could reach our destination in about 17 years. And in another 4 years, when the signal from it reaches Earth, we'll know if there's an advanced civilization. Another possibility for faster-than-light travel is the warp bubble spacecraft. The spacecraft would have to compress space in front of it and stretch it behind its tail. Then we'll be able to reach any point in the universe in literally a few seconds. But such travel remains a fantasy for us. Perhaps we can get to different corners of the universe through wormholes. They're shortcuts similar to tunnels, but there's one problem. These wormholes might be inside black holes. They're the most mysterious objects in the universe. They're so heavy that even light can't escape their trap. Our spaceships wouldn't stand the tension either. There's also a theory that Earth is unique because it was born under completely accidental circumstances. 4.5 billion years ago, our planet was a block of lava that began to cool and solidify. But its tranquility was broken by an asteroid the size of an entire planet flying by. The collision occurred at such an angle that the Earth was not completely destroyed, but part of the asteroid remained in our orbit. A heavy rock near our planet stabilized Earth's rotation, and the gravitational interaction with the giant debris caused our core to heat up. In addition, the asteroid brought a lot of water to Earth. Such a collision is extremely unlikely. It's like winning the lottery, many times in a row. But so far, we have no reason to believe life in outer space exists. Just as we have no reason to believe that there's no advanced civilizations in the universe, except for ours.
It was the year 2017 when astronomers spotted a bright star hurtling out of the Milky Way. It was moving incredibly fast at a speed of 2 million miles per hour. That's almost 4 times as fast as the Sun orbits around the center of our home Milky Way galaxy. It takes our star more than 225 million years to complete one journey. Anyway, back to our star, the Wanderer. The main issue with it was that it was moving against the direction in which most stars travel around the center of our galaxy. Even more bizarre, it consisted of totally different star stuff. Astronomers managed to identify its composition. The star was made up of heavy metallic atoms. At the same time, most of the other stars consist of way lighter elements. The wandering star got the name LP-40-365. It was moving so fast that it literally dashed out of our galaxy. This made scientists believe that the space traveler was pushed out of its place by some kind of cosmic disaster, like a supernova. A supernova is the largest explosion that can take place in space, an explosion of a star. It happens after irreversible changes start in the core of a star. Supernovas can occur in 2 ways: in binary star systems and when there's a single star. Binary stars are 2 stars orbiting around the same center. At some moment, one of the stars, a very dense white dwarf, starts stealing matter from its companion. After some time, this thief accumulates too much matter, which causes it to explode into a supernova. Or it can be a single star nearing the end of its life. It's running out of its fuel. More and more mass is flowing into the core of the star. In the end, the core becomes so heavy that it fails to withstand its own gravity. After the core collapses, a tremendous amount of energy is released in a supernova. But astronomers still can't figure out how a supernova could send LP-40-365 flying. There are more questions than answers. Was it a companion star that got flung out by a shockwave created by a supernova? Or was it a piece of the exploded star? A new study based on the collected data has shown that the star, which is a white dwarf, keeps slowly rotating around its axis. Astronomers are almost sure it means LP-40-365 is indeed just a chunk of space debris, and not a full-fledged star. This wandering piece somehow managed to survive one of the fiercest space events. But after making such a conclusion, scientists realize something amazing. LP-40-365's unusual features could appear after the star witnessed a supernova. Even though this event happened lightning fast, the entire makeup of the star got changed. Most stars consist mainly of helium and hydrogen. But LP-40-365 is different. It contains such heavy elements as magnesium, oxygen, and neon. It must have been the supernova that added these atoms to the star's composition. By the way, astronomers consider all elements that are heavier than helium to be metals. This means that after witnessing the supernova, LP-40-365 became metallic. Right now, the star doesn't have its own planets, but NASA's Transiting Exoplanet Survey satellite, which is on the lookout for distant planets passing in front of their host stars and dimming them, has noticed a curious thing. LP-40-365 brightens and then dims again every 8.9 hours. It might mean that the star pulsates, but usually stellar pulsations are much less regular. A more plausible explanation is that the star's surface is uneven, and as it spins, sunspots are brought into and out of view. And it's great news, because after astronomers figure out how fast the star rotates, they can understand what happened to it around 5 million years ago during the supernova. Bright blue exoplanet HD 189733b looks peaceful and eerily familiar. Doesn't it resemble Earth? But this appearance conceals the planet's terrifying nature. There, the winds blow at 5,400 miles per hour. It's 7 times the speed of sound. But that's not the worst. It rains glass, sideways, in this scorching hot world. Neutron stars are ultra-dense collapsed cores of giant stars. They emit X-rays or radio waves. But in 2018, astronomers discovered a weird stream of infrared light. It seemed to be coming from a neutron star 800 light-years away from our planet. The most plausible theory is that this signal was probably produced by a disk of dust surrounding the star. But there isn't enough evidence to confirm this idea. Mercury is the fastest planet in the solar system. It zips around the sun at a breakneck speed of more than 100,000 miles per hour. That's around 40,000 miles per hour faster than our home planet. It's one of the reasons why a year on Mercury equals 88 days on Earth. Mercury is the planet that orbits the closest to the sun. That's why if you were standing on its surface at its closest approach to our star, the sun would look more than 3 times as large as it does on Earth. The Black Widow pulsar is a rotating neutron star that is munching on its partner, which is a lightweight brown dwarf star. The more material the pulsar consumes, the more slowly it spins. The energy the neutron star is losing in the process causes the companion star to dwindle. There's a stellar nursery in the constellation Centaurus, and even though this place is called a nursery, it's anything but peaceful or safe. It's made up of hydrogen and newborn stars and is located in a nebula around 6,500 light-years away from Earth. A nebula is a giant cloud of gas and dust floating in space. The intense energy baby stars emit makes hydrogen clouds glow ominous red. This energy is so powerful, it's eating away dark clouds of dust. Astronomers can see them disappear like lumps of butter on a hot frying pan. Faraway Neptune-sized exoplanet Gliese 436b is a paradox. It's made of scorching hot ice, and this ice is burning. The planet completes one full orbit around the red dwarf Gliese 436 in just 2 days. It means the exoplanet travels very close to its parent star. That might be the reason why the planet's temperatures rarely drop below 800 degrees Fahrenheit. But the strangest thing? The planet hosts huge volumes of water ice known as Ice X. And this ice remains solid despite such incredibly high temperatures. Jupiter is the largest planet in the solar system. It's 318 times as massive as Earth. It's also 2.5 times as massive as all other planets of the solar system combined. But here's a paradox. If this gas giant got even more massive, it'd actually become smaller. The added mass would make the planet denser, and this would cause it to start pulling in on itself. Astronomers claim that Jupiter can eventually end up being 4 times as massive as it is now. But at the same time, its size won't change. DGSAT-1 galaxy is as big as the Milky Way, but it's nearly invisible because its stars are spread out incredibly thin. But what makes the galaxy so unique is that it's sitting all alone. unlike other galaxies of this kind. Those are usually found in clusters. It can mean that DGSAT-1 was formed in a different era, probably a mere 1 billion years after the Big Bang. If it's true, the galaxy is a real living fossil. Saturn's moon, Hyperion, is one of the most bizarre-looking moons in the solar system. But the appearance isn't the strangest thing about this space body. The pumice stone-like rock is pockmarked with countless craters, and it's also charged with static electricity, which is flowing out into space. About 4,000 light-years away from Earth, there's a planet that seems to be one enormous diamond. The planet is denser than any other discovered so far and consists mostly of carbon. It's so dense that astronomers think this carbon might be crystalline. It means that at least some part of the planet is diamond. Ceres is the most massive space body in the asteroid belt between Jupiter and Mars. It totals almost a third of the entire mass of the whole belt. But at the same time, Ceres is the tiniest of the dwarf planets out there. It's also the only dwarf planet that dwells in the asteroid belt, and also the only one that is located in the inner solar system. Astronomers sometimes call Jupiter a failed star. The gas giant indeed contains a lot of helium and hydrogen. But its mass isn't enough to start a fusion reaction in its core. And that's exactly how stars produce energy. They fuse the atoms of hydrogen together under extreme pressure and heat and create helium. In the process, they also release light and heat. Jupiter could start a nuclear reaction and become a star only if it was 70 times its current mass. Space is completely, eerily silent. That's because in the vacuum of space, there's no atmosphere, and the sound waves need some medium to travel through. That's why worlds with atmospheres like Earth are full of noise. Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Even so, just one minuscule thing would have enough mass of 1,000 sedans. One theory claims that tons of micro black holes could be created right after the Big Bang. Some scientists even go so far as to say that a couple of mini black holes pass through our planet every day. Every hour, the sun sends more energy to Earth than our planet uses in a year. Even though people are now using much more solar energy than a decade ago, it's still a mere 0.7% of the world's annual electricity usage. There might be moons orbiting other moons, but astronomers haven't agreed on this theory yet. Planets orbit stars, moons orbit planets. But why can't there be moons, also known as submoons, moonettes, and moons? Researchers claim that moons could exist, but the host moon has to be massive enough and the moon small enough. There must also be a large distance between these moons and the host planet. Jupiter is the most massive planet in the solar system. This means its gravity is also the most intense. It's 2.5 times as great as what we have on our home planet. Once, the gas giant's gravity even tore apart a large comet called Comet Shoemaker-Levy 9. Then the planet eagerly swallowed the chunks of the former comet. If you were standing at the equator on Mars, the temperature at your feet would feel like that of a warm spring day, but your head would be literally freezing. Lost in space and drifting through galaxies, rogue planets were once flung away from their parent stars, but one of them, floating 200 light-years away from Earth, is different from the rest. It's a planet-sized object with a magnetic field 200 times stronger than that of Jupiter. This field is so powerful that it generates never-ending flashing auroras in the planet's atmosphere. Europa is one of Jupiter's largest moons, even though it's smaller than Earth's moon. But the cool thing about this satellite of the gas giant is that it's covered with ice. And some of this ice is smooth, which means you could skate there. And a 3-foot axle jump you can perform on our planet would take you 22 feet into the air. At the same time, the landing speed on Europa would be the same as it is on Earth. Haumea, a dwarf planet orbiting the Kuiper Belt, has a bizarre elongated shape and 2 moons. The day on this planet lasts 4 hours, making it the fastest spinning large object in the solar system. But the most mysterious thing about Haumea is that the planet has a thin 40-mile-wide ring circling it. Astronomers haven't managed to figure out how or why it appeared around the dwarf planet. 11 Earths could fit across the equator of Jupiter, and if our planet was the size of a grape, the gas giant would be as large as a basketball. 9 spacecraft have already visited Jupiter. 7 of them just flew by, and 2 orbited the huge planet. The most recent of them, Juno, arrived at Jupiter in 2016. The craters of the Moon's south pole are likely to be the frostiest place in the whole solar system. The crater's floors are always in the shadow. That's why the temperature never rises above 397 degrees Fahrenheit, even during the day. If you decided to fly a plane to Pluto, your journey would take around 800 years. You'll find the highest mountain in the solar system on an asteroid called Vesta. Its peak rises 14 miles above the base of the mountain. This makes Rhy Silvia, that's what the mountain is called, almost 3 times taller than Everest. Saturn's rings weren't discovered all at once. It happened gradually. That's why they were named alphabetically in the order scientists found them. Now they go like this: D, C, B, A, F, G, and E. A day on Venus is around 243 Earth days long. But the bad news is that you'd have to wait for a weekend for 3 years. All because a day on Venus is longer than its year. A solar phenomenon called terminator events is taking place at the Sun's equator. Disastrous magnetic field collisions seem to cause ginormous twin tsunamis of plasma. These tsunamis tear across the star's surface, moving at a speed of 1,000 feet per second. They can last for weeks at a time and happen almost every decade. The winds on Neptune are the fastest in our solar system. Most of them can reach the speed of 1,600 miles per hour. Almost any of these enormous storms could easily swallow our entire planet. The 18th brightest star in the night sky, Fomalhaut, is a terrifying sight. It's dubbed the Eye of Sauron because a ring of dust and debris circling it makes it look like a giant eye staring into your soul. The intimidating star is more than twice the mass of our Sun and is 25 light-years away from Earth, which isn't that far away considering distances in space. Mars has 2 moons, Phobos and Deimos. In the next 30 to 50 million years, the planet's gravitational forces will tear Phobos apart. It'll probably result in the formation of a ring around Mars. An asteroid the size of a car enters the atmosphere of our planet every year. Such an intruder could wipe out a small town off the face of the Earth. Dust and smoke would rise into the atmosphere, preventing sunlight from reaching the surface of the planet. It would cause the temperatures all over the world to drop and the climate would change. Luckily, such asteroids burn in the atmosphere before they even come close to the surface. The radio signal produced by a spacecraft when it contacts Earth is less powerful than a light bulb in your fridge. By the time this signal reaches our planet, its power is only 1/10000000th of a watt. No wonder that antennas gathering these super weak signals are huge. The Deep Space Network that detects signals from spacecraft has dish antennas that measure up to 230 feet across. That's more than the width of a soccer field. In 1999, NASA lost a Mars orbiter because one engineering team was using the metric system, and another was doing calculations with the help of the imperial system. Nebulas are giant clouds of gas and dust. With time, gravity starts to pull these clumps of dust and gas together. They grow larger and larger, and their gravity gets more powerful. One day, a nebula's mass becomes so great that it collapses under its own gravity and forms a new star. Around 4,000 light-years away, in the constellation of Scorpion, there is the Butterfly Nebula. Its wingspan is greater than 3 light-years, and the structure inside the nebula is one of the most complicated ever observed. The nebula's central star, a white dwarf, is heated to an insane 450,000 degrees Fahrenheit. This means it was formed from another huge star, likely more than 5 times the size of our Sun. The white dwarf is surrounded by a thick disk of dust and gas at the equator. That's what probably makes the whole structure look like an hourglass or a butterfly. If you decided to lump together all the known asteroids in the solar system, their total mass wouldn't exceed even 10% of the mass of our moon. A cloud of water vapor is floating in space. It surrounds a supermassive black hole 12 billion light-years away from Earth. The cloud contains 140 trillion times the entire volume of water on our planet. Astronomers think this water cloud appeared just 1.6 billion years later than the universe itself. The densest objects in space are neutron stars. They're the size of a small city, yet their mass is about 1.4 times the mass of our Sun. A single teaspoon of neutron star material would weigh 1 billion tons. And a neutron star's gravity is 2 billion times stronger than the gravity of our planet. In 1993, the Galileo probe was traveling past a miniature asteroid. It was no more than 20 miles across, and still, the tiny thing had a 1-mile wide moon. Astronomers have discovered tons of moons orbiting minor planets in the solar system since then. We live inside the Sun. The star's atmosphere stretches way beyond its visible surface, and our planet is well within its reach. That's how the gust of the solar wind creates such a breathtaking phenomenon as the northern and southern lights.
Weird, unusual sounds out of nowhere are spreading all over our galaxy, constantly repeating, and it's something we've never heard before. Scientists discovered it in 2020, and it was nothing like any of the other energy signatures they ever studied. Powerful and bright radio signals occurring from time to time, mysteriously disappearing within a day. It doesn't fit the profile of any space body we know. The signal is a bit irritating, and it disappears without a schedule. When scientists tried to match the signal with some other telescopes, it was gone. Low-mass stars sometimes flare up with radio energy, but not here, since they mostly have X-ray counterparts. Very dense collapsed stars, like pulsars and magnetars, are also not a choice. The closest solution they got is a mysterious class of objects we know as the Galactic Center Radio Source, GCRT. It's a radio source that brightens and rapidly glows. It decays near the center of our galaxy and could help us unravel the mysteries of the universe. If you had a flying car that could go up at a speed of 60 miles per hour, you'd only need 1 hour to get into space. The moon is a little bit farther, 250,000 miles, which is about 10 times the circumference of our planet. That means a moon trip would be like taking a tour around the globe and doing it 10 times straight, which would take less than 6 months. A trip to Pluto would take over 800 years. Proxima b is the closest Earth-like neighbor we have. It's a small rocky world that orbits the closest stellar neighbor of our Sun. It orbits the star's habitable zone, an area that's far enough from any star to have moderate conditions, not too cold and not too hot for liquid water to at least hypothetically exist. If you tried to travel to Proxima b at a speed of 25,000 miles per hour, which is the speed of the Apollo moon rockets, it would take you over 112,000 years to get there. You might not be able to breathe there. No one knows if Proxima b has an atmosphere. Humans explore the universe all the time, but we can only see around 5% of the matter up there. And Albert Einstein was the first one that realized the empty space is not really nothing. The rest we can't see is actually made up of invisible matter, also known as dark matter. It's about 27%, combined with something called dark energy, which is 68%. If you try to pour water into space, of course, outside of a spacecraft, it would immediately boil away or vaporize. That's because there's no air or air pressure in space. As air pressure lowers, the temperature you'd usually need to boil water at also gets lower. Keeping that in mind, water boils way faster on a mountaintop than, for example, at sea level. There's no air pressure in space, so water could boil at a very low temperature. Scientists believe that there are at least a couple of billion galaxies out there. We don't know the real number, and probably never will, but they tried to calculate it by counting how many galaxies we can see in a pretty small and restricted area of the sky. It may seem as if the universe was filled with stars and a couple of planets here and there, but our home galaxy has at least 100 billion planets. If you fill a balloon with helium and release it, you'll notice it floats very high. It'll go up into the atmosphere, but it won't go into outer space. The higher you go, the thinner the air in our atmosphere gets. Your balloon will rise up until the point where the atmosphere surrounding it has the same weight as the helium inside it. That will happen at approximately a height of 20 miles above the surface, so this is as far as a helium balloon can rise. We don't really know how big the universe is. We can't see its edges, nor do we know if it even has an edge. We use technology to see out to a distance of around 14 billion light-years from our planet. This means we can see around 28 billion light-years in diameter across, starting with the outermost layer of our atmosphere that ends at around 600 miles above our planet's surface. Although the size of the universe is constantly changing and gets bigger through time. Mercury is closest to the Sun, so most people think it's the hottest planet too. Still, Venus is the hottest planet. It's the second planet away from our central star, around 30 million miles farther from the Sun compared to Mercury. Mercury doesn't have an atmosphere, which is like some sort of a warming blanket that helps maintain the heat coming from the Sun. Venus has an unexpectedly thick atmosphere, around 100 times thicker than the one we have. Its atmosphere doesn't let the heat out, it just keeps it and constantly makes Venus hotter and hotter. Also, it mostly consists of carbon dioxide that freely lets solar energy in. But it's less transparent to lose long wavelength radiations that the warm heated surface emits. The average temperature there is around 875 degrees Fahrenheit, which is hot enough to melt tin. The maximum temperature on its neighbor, Mercury, is 800 degrees Fahrenheit. In maybe 2 or more billion years, it will be way too hot for life to exist on our precious planet. As the hundreds of millions of years go by, our sun will keep getting hotter and brighter. Eventually, temperatures will be so high, our beautiful oceans will be wiped away. Since they produce 70% of the oxygen we need to survive, there'll be no life without them. All of this means that our planet will simply become a vast desert, something like Mars is today. Pluto, a very distant used-to-be planet, now dwarf planet, is actually smaller in diameter than the entire US. The biggest distance there, from Maine to Northern California, is approximately 2,900 miles, while Pluto is only 1,473 miles across. Pluto is very far, but the edge of our solar system is 1,000 times farther away than this dwarf planet. But astronomers found many space objects orbiting our sun way farther than Pluto, such as Kuiper Belt objects and trans-Neptunian objects. There's also an Oort comet cloud that goes half a light year from Pluto, also 1,000 times farther. A neutron star is really heavy. Just a teaspoon filled with it would weigh 6 billion tons. Neutron stars are something that remain from huge stars that have run out of fuel. The fading star explodes, and its core falls apart, but due to gravity, it forms an extremely dense neutron star. These stars typically have a mass of up to 3 suns, but the radius there is around 6 miles, because this is one of the densest things in our universe, at least that we know about. The universe has a color, and it averages to be some kind of beige, or as they call it, cosmic latte. It also has its own smell that reminds you of seared steak or hot metal. At least, that's something astronauts floating in space have said. If you want to build a spacesuit, get ready to work really hard. It takes 5,000 hours to make it and will cost you $1 million. A really good one will have 11 layers of material and weighs about 110 pounds, and it needs to be comfortable. You'll need more space in there because you grow up to 2 inches when in space. When you're floating around in space, Earth's gravity doesn't have any impact on you. That's why the vertebrae in your spine might expand and relax a little bit, which means you'll be maybe 3% taller. For 6 feet, it's about 2 extra inches. Oh, don't worry, it's not permanent. As soon as you go down to Earth, you'll shrink back down to your normal size within a couple of months. Space isn't the best option if you want to have a conversation with your friend. Because up there, sound doesn't travel at all. Molecules there are so far apart that sound vibrations can't reach them, which automatically means they can't vibrate, so we can't hear them. Movies are not accurate with this. No one could hear you screaming in space, too. We kind of live inside our sun. The sun is not just that big hot ball of light located 93 million miles away from us. Its outer atmosphere is way bigger. It extends far beyond the surface we can see. Our planet's orbit goes through its tenuous atmosphere. The evidence is when gusts of the solar wind generate the southern and northern lights. That means, in some way, we live inside the sun. Not just us, other planets too, including distant Neptune. The heliosphere, which is what we call the outer solar atmosphere, extends to about 10 billion miles. You're in your galactic space cruiser on your way to Outpost 52, delivering supplies for the small colony there, when alarms begin going off. You scan your displays, but something catches your eye before you can work out what's happening. You don't need a view screen, as the front section of your ship is transparent, like a one-way mirror. A colossal orange and purple cloud is sweeping towards you. There's no time to analyze it. You put the ship into a dive, as steep as it will go. The alarms go crazy, but you're too focused on getting out of danger. The ship rattles, and you think it will break up, but your ship is fast and powerful, and somehow you manage to get underneath it. You look up and see the gigantic plasma cloud go soaring past. Curiosity has bitten you, and you decide to follow it. You program your computer to analyze it. Soon the information is coming back, and you can't believe what it's telling you. This plasma cloud is a wrecker of galaxies. It and others like it have been ending galaxies before their time. You recall your studies back on Earth when you were just a young pilot. There have been studies as far back as the 21st century as to why galaxies were mysteriously ceasing the formation of new stars, causing them to end ultimately. Stars form from thick clouds of gas that have become extremely cold. They condense and, over time, collapse into solid compact matter. There's a famous photograph taken by the Hubble Space Telescope. Most people have seen it. It's called the Pillars of Creation. It's the Eagle Nebula, where stars are forming. They call these environments star nurseries. It's a pretty cute concept if you think about it. But there's a bad guy lurking, and you're following it. It's a vast star wrecker. The wrecker rushes in and sweeps the gas out of these star-forming galaxies at an accelerated rate, preventing stars from forming in the first place. It's like a giant broom. But rather than cleaning up, it's ceasing up, bringing new galaxies to a premature end. Now that you know how dangerous it is, it's best to hang back a bit. Let's see if we can see it in action from a safe distance. It had been a long-standing mystery why some galaxies don't birth new stars. The star wrecker is smart. It hangs around large galaxy clusters. There's one in particular, the Virgo cluster. This is the one that scientists studied and came across the star wrecker. The nearby Virgo cluster is 7 million light-years across and contains thousands of galaxies. When I say nearby, it's about 65 million light-years from us. Not exactly a weekend space cruise away, but it's pretty close in galactic terms. The cluster hurtles through the superheated plasma at speeds of up to 1 million miles per hour. The cluster forms the basis for the large Virgo supercluster, of which the local group, where our Milky Way resides, is a member. Its proximity to us makes it easier for scientists to study. It's also one of the most extreme regions of the universe that we know of, currently. Who knows what else is out there? The Virgo cluster is also unusual, as it's still forming new stars, and we can observe them, such as in the famous Hubble nursery photo. A galaxy in this cluster is called the Messier 87. It was discovered way back in 1781 by a French astronomer named Charles Messier. It looked a bit fuzzy to him, so he called it a nebula. a nebula without stars. More information on what it was couldn't be ascertained until the 1920s. Messier was well respected and in his lifetime discovered 13 comets. He was born in rural France, the 10th of 12 children. When he was 14, he witnessed a tremendous six-tailed comet in 1744. It was astonishing and was visible to the naked eye for several months. Its effects were dramatic and unusual. It was so bright that it's been recorded as the sixth brightest in history. 4 years later, young Charles saw a solar eclipse from his hometown on the 25th of July, 1748. He knew then that he wanted to explore the world of astronomy. It was meant to be. A lunar crater and an asteroid have been named after him. Nothing is mighty, however, like the Messier 87, or M87. It's a supergiant elliptical galaxy with trillions of stars. It's the second brightest galaxy within the northern Virgo cluster, making it popular amongst astronomers and amateur enthusiasts. Elliptical galaxies are older, low-mass stars with minimal star formation activity. Large numbers of globular clusters surround them. They make up roughly 10 to 15% of the Virgo supercluster. M87 has a supermassive black hole at its core. The black hole was photographed using data collected in 2017 by the Event Horizon Telescope, EHT. It was announced excitedly to the world in 2019. In March 2021, the EHT collaboration revealed a polarized-based image of the black hole for the first time. It was a pretty exciting event. It was the first time that a black hole had been captured. It happened all thanks to the Event Horizon Telescope, which is many radio observatories or radio telescope facilities around the world, all working together to produce a highly sensitive and high-resolution telescope. Another array of telescopes in Chile is called the Atacama Large Millimeter Submillimeter Array, ALMA. They captured high-resolution images of the 51 significant galaxies in the Virgo cluster. That's part of how we know what we know. M87 and other galaxies don't appear to be doing a lot to the naked eye. In fact, in a typical human lifetime, they barely move at all. Yet they are made up of gas, dust, and other objects that move through space at high speeds. They move when affected by the gravity of other galaxies or dark matter, a mysterious entity that is 5 times more common than ordinary matter. Many galaxies, including our own, are believed to have a halo of dark matter surrounding them. The dark matter can pull more significantly on the smaller galaxies outside the clusters. As the galaxy gets dragged around through space, the star wrecker may come across. Giant clouds of intergalactic plasma, a form of electric gas, can behave like an atmosphere and drain the gas inside the galaxy. It sweeps out the gas inside the galaxy, stripping it of what it needs to make stars. It's hard to grasp the scale of this sort of activity, but that's what scientists now believe has been occurring to some galaxies or the nebulae without stars, as Charles Messier saw it. Now, let's park our space cruiser here and watch this thing in action. What we've been calling star wrecking is known as gas stripping. It's one of the most spectacular and violent external events in space. A scientist from the National Research Council of Canada said that galaxies are moving so fast through hot plasma in the cluster that a vast quantity of cold molecular gas is stripped from the galaxy. It's as though the gas is being swept away by a giant cosmic industrial blower. It's not the sort of clean-out we want to happen in our galaxy. You observe it in action. You're impressed, but equally respectful of its great power. The gas stripping, also known as ram pressure stripping, travels through many galaxies and removes a star-forming gas. The process is very efficient. The gas is behaving differently from the clouds in our galaxy. They aren't forming as many stars as they are in ours. A 21st century study found that the same process happens in smaller groups of only a few galaxies, with much less dark matter. The study looked at a staggering 10,567 satellite galaxies. These are galaxies that exist beyond the enormous galaxy clusters. Most galaxies in the universe exist in between 2 and 100 galaxies. They were able to study such a large number by using stacking. It makes it possible to learn about a collection of faint objects by combining all the information from the objects and making an average characteristic. They ultimately determined that gas stripping, or star wrecking, is potentially the main way that galaxies, predominantly star formation, are shut down by their surroundings. Pretty unfortunate to have such a nasty neighbor. So, now that your curiosity has been satisfied, it's best to leave this plasma cloud and get on with your journey to Outpost 52. You're going to be late now and could be in a whole lot of trouble. While the cruiser turns around, we'll head back to Earth. And back in time, back to 1744, to that night in rural France, where a teenager stood outside, marveling at the night sky and the spectacular vista of the six-tailed comet. And from that moment, was inspired to begin a lifelong quest based on a single question. Perhaps the ultimate of all. What's out there?
During the recent years, scientists made 2 breakthrough discoveries about our universe. Thanks to new technologies, we've looked into the distant past. And we've learned something that can change our understanding of the universe forever. What are these discoveries and what do they mean to us? Let's find out. Recently, we unveiled the first color image from the James Webb Space Telescope. It's a mind-bending photo capturing thousands of ancient galaxies. This oldest documented light in the history of the universe dates back over 13 billion years. That's just 600 million years after the Big Bang. It's like getting a sneak peek into the universe's baby album. But that was just the beginning. Astronomers were expecting to see some tiny young galaxies. But what they found was a real surprise. Impossibly early, impossibly massive, and all that from just a tiny red dot. The lead author of the study, Ivo Laba, was working at the computer as usual, and suddenly he got 2 numbers. Age, 13 billion years. Weight, 100 billion stars. When he realized what that meant, he nearly spit out his coffee. But that red dot was just the beginning. The next day they found 5 more galaxies just like this. Turns out, these 6 massive galaxies are as old as the Milky Way itself. The entire research team was in disbelief. They were like, wait, what? These guys couldn't be that mature so early in time. Did we make a mistake? But nope. The James Webb Space Telescope, the new cool guy on the space block, just has some serious skills. It can see through dust clouds with its infrared vision and spot galaxies that were previously invisible. Move over Hubble. There's a new stargazer in town. But why is it shaking things up so much? Because this discovery affects our understanding of how galaxies formed. Let's try to explain. A long time ago, 13.8 billion years ago to be precise, our universe was born. It was chilling out for a while, and then it started to form the first galaxies. And these galaxies were full of gas and dust. Eventually, this gas started turning into stars. Some galaxies were more massive and had more stars, and some were lighter and had almost no stars at all. In any case, they all grew gradually. The stars in them were born slowly and smoothly. That's how our current models explain this. But these new observations from the James Webb Space Telescope show an unexpected surprise. Looks like, even in the early universe, our ancient friends had lots of stars. More than what we would ever expect. If that's the case, then these galaxies are like the overachievers of the universe. They skipped the small and gradual growth phase and went straight to being giant universe breakers. According to our current cosmological model, they shouldn't even exist. But they do, so it looks like after the Big Bang, the stars were forming much faster than we thought, which is pretty weird. This could mean that there's something missing in our understanding of the galaxy formation. As you can see, these universe breakers are really living up to their name, causing a potential total consensus among scientists. The universe was like, hey, I'm about to flip cosmology models upside down. But let's not jump to conclusions. There are many theories that could explain these mind-boggling discoveries without breaking the standard model. For example, maybe the light we're seeing isn't coming from stars at all, but from the swirling disks of doom around supermassive black holes. These colossal cosmic beasts can gobble up matter and spit out a dazzling light show. And James Webb Telescope's keen eye is picking up on these enigmatic accretion disks like never before. Or maybe these galaxies could be playing hide and seek with us. Maybe there's more to the story that we haven't seen yet. After all, the universe is vast and mysterious, and we've only just begun to scratch the surface. And whoa, we really need to slow down here. Before we even try to explain all this stuff, we need to confirm whether these ancient galaxies really are that old. Although even if they're actually just supermassive black holes, it still shows an astounding change. We'll have to wait about a year to find out. One thing's for sure, the James Webb Space Telescope has definitely taught us a valuable lesson. Expect the unexpected. And this is just the beginning of unexpected. Evolab's team wasn't the only one who made such a huge breakthrough. There's also a team that claims that they've unlocked the secrets of the universe's past, and that's worth 2 Nobel Prizes. Move over James Webb Space Telescope, because this discovery came from an antenna that's smaller than a fridge and costs less than $5 million. Talk about space bargain hunting! The astronomers caught this signal that showed some surprises. It was coming from the earliest stars of our universe, back in the days when they were just beginning to twinkle. Say hi to our celestial ancestors again. Now, the signal was pretty weird. The temperatures were unusually low, and there was a pronounced wave that left astronomers scratching their heads. What could be causing all this? Well, there's a theory. Dark matter may have been at work, and if that's the case, then we can really be on the verge of a great discovery. Imagine you're looking at the night sky filled with stars, but there's something else there that you can't see. It's like an invisible cloak that covers the entire universe. Scientists call this mysterious stuff dark matter. Dark matter is like the ghost of our world. It doesn't emit, absorb, or reflect any light. We can't see it with telescopes or our eyes. That's why we call it dark matter. But if we can't detect it in any way, how do we know it exists? Because of its gravitational pull. One day we noticed that our understanding of how galaxies were created was incorrect. According to our calculations, they should have been some chaotic gas, but something held them together, turning them into spirals, like some kind of invisible glue. Then we thought, maybe this invisible glue really exists. If the moon was invisible, we would still suspect that it exists somewhere because its gravity affects the tides on Earth. This is also the case with dark matter. Its gravity influences the motion of galaxies and other cosmic objects. In fact, dark matter makes up a huge chunk of the universe, about 27% of it. Moreover, the normal matter we can see, like stars, planets, and galaxies, only make up about 5% of the universe. So even though we can't see dark matter, there's actually more of it in the universe than everything we can see. Scientists are still trying to figure out if dark matter exists and what it can be made of. Some theories suggest that it could be made up of exotic particles that are different from the particles that we're used to. Others think that it might be some kind of weird, undiscovered form of matter that doesn't interact with light at all. Anyway, it's an intriguing mystery, and if we ever confirm the existence of dark matter, our understanding of our world will change forever. So now you can understand why the excitement in the scientific community is palpable. If this discovery is confirmed, then we will get the first real proof of dark matter. This discovery may be even more important than the Big Bang itself because, as astronomers put it, we are made of star stuff, and so we are glimpsing at our origin. But of course, we still have to wait and explore all this in great detail. In science, one should never rush to conclusions. And while scientists study this stuff, we'll be here, on the edge of our seats waiting for the next space blockbuster to unfold. The universe never ceases to amaze us with its wonders. Who knew that such a small and humble antenna could unlock such cosmic secrets? It just goes to show that in the vastness of space, even the tiniest discoveries can have the biggest impact. Keep looking up, and who knows what other cosmic surprises are waiting to be uncovered.
Bang! Or should I say, Big Bang. The Big Bang. Ahem. So, after the Big Bang, the universe resembled a hot soup of protons, neutrons, and electrons. After it started to cool down, the protons and neutrons began to combine, first forming ionized atoms of hydrogen and later some helium. These ionized atoms of helium and hydrogen attracted electrons, turning them into neutral atoms. As a result, the light was able to travel freely for the first time ever, since it was no longer scattering off free electrons. What does it mean? The universe was no longer dark. At the same time, it was still about a few 100 million years after the Big Bang before the very first sources of light started to appear. That's when the cosmic dark ages came to an end. We don't know for sure what this universe's first light looked like or how the first stars formed. Luckily, we have the James Webb Space Telescope to help us find the answers. How come? All because this is an infrared telescope. Why is it important? Let's figure it out. Imagine a star. It's a very, very old star, maybe the first star out there. Light leaves this star 13.6 billion years ago and settles off on an incredible journey through space and time. It needs to get to our telescopes. By the time this light reaches us, its color or wavelength shifts towards red. That's something we call a redshift. It happens because when we talk about very distant objects, Einstein's theory of general relativity comes into play. According to it, the expansion of the universe also means that the space between objects stretches, making them move away from one another. But that's not all. Light stretches too, which shifts it to longer wavelengths. Eventually, this light reaches us as infrared. In other words, redshift means that light that is originally emitted by the first stars or galaxies as ultraviolet or visible light gets shifted to redder wavelengths by the time we catch a glimpse of it here and now. For the farthest objects with very high redshift, that bare minimum of visible light is shifted into the near and mid-infrared part of the electromagnetic spectrum. That's why to see those space objects, we need a super powerful telescope. And if we talk about the Webb telescope, it can see back to about 100 million to 250 million years after the Big Bang, which is incredibly awesome. So by observing the universe at infrared wavelength, James Webb lets us see things no other telescope has ever shown before. The primary goal of this incredible piece of equipment is to study the formation of galaxies and stars that formed in the early universe. To look that far back in time, we need to look deeper into space. All because it takes light time to travel back from there to us. So the farther we look, the further we glimpse back in time. To find the first galaxies, James Webb is going to make an ultra-deep near-infrared survey of the universe. Then it'll follow it up with a few other methods of research. Now, as you remember, the gas between stars and galaxies in the early universe was opaque, and energetic starlight couldn't penetrate it. But then, about 1 billion years after the Big Bang, it suddenly became completely transparent. Why? The James Webb Telescope might have found the reason. At one point in the past, the first galaxy's stars emitted enough light to ionize and heat the gas around them. This helped clear the view over hundreds of millions of years. The newest insights scientists got were about a time period called the era of reionization. That's when the universe underwent some dramatic changes. After the Big Bang, gas in the universe was unbelievably hot and dense. Hundreds of millions of years passed, and it cooled down. But then, something baffling happened. It was as if the universe hit the repeat button, and the gas became ionized and hot once again. It could have happened because of the formation of early stars. After that, millions of years later, this concoction became transparent. For a long time, researchers have been hoping to find definite evidence that could explain these changes. And now, the telescope has finally shown that those transparent regions are located around galaxies. Astronomers have seen these galaxies reionize the gas surrounding them. Even better, they've managed to measure how large these transparent regions are. They're ginormous compared to the galaxies themselves. Imagine a hot air balloon, and now imagine a pea floating inside. You've got it, and guess what? These tiny galaxies drove the entire reionization process, clearing huge regions of space around them. These transparent bubbles kept growing until they merged and caused the entire universe to become transparent. The research team chose to target a period of time before the end of the era of reionization. At that time, the universe was not quite opaque, but not quite clear either. It was a patchwork of regions of gas in different states. To find out this cool fact, the astronomers aimed the James Webb Telescope in the direction of a quasar, an incredibly bright space object. It acted as a giant flashlight, traveling towards us through different regions of gas. It was either absorbed by the patches of near opaque or moved freely through the areas where the gas was transparent. The scientists then used Webb to examine galaxies in that region of space. They found out that these galaxies were usually surrounded by transparent regions with a radius of about 2 million light-years. For comparison, the area the galaxies cleared was almost the same distance as the space between our home Milky Way galaxy and our nearest neighbor, the Andromeda galaxy. And the telescope witnessed those galaxies in the process of clearing the space around them. It was the end of the era of reionization. Until then, no one had evidence of what caused reionization. The team is planning to dive into research about other galaxies in 5 additional fields. The Webb telescope's results from the first field have been overwhelmingly clear. And even though the astronomers had expected to identify a few dozen galaxies existing during the era of reionization, they actually managed to spot 117. Now, let's talk a bit about the main hero of today's show, the James Webb Space Telescope. It's an absolutely stunning piece of equipment which is around 100 times more powerful than the Hubble Space Telescope. And the latter has observed places that are 13.4 billion light-years away. The James Webb Telescope is also on the pricey side, to put it mildly. Even though originally the cost of the telescope was estimated to be just $1 to $3.5 billion. The whole development process cost around $10 billion. For comparison, it cost NASA $4.7 billion to build and launch the Hubble telescope, and it was another $1.1 billion to fix it in orbit. Even though the James Webb Telescope itself is 3 stories high and the size of a tennis court, its mirrors are the lightest large telescope mirrors of all time. During the manufacturing process, they underwent a 92% reduction in weight. When you look at them, the telescope's mirrors seem to be gold, but in reality, they're made of beryllium. This is a steel gray, lightweight, and brittle metal. A gold coating is applied to each mirror, that's true, but they can't be produced entirely out of gold, since this precious metal tends to expand and contract, even with small temperature changes. So the total amount of gold in the James Webb Space Telescope is less than 2 ounces. That's a golf ball-sized piece of gold. And the gold plates covering the mirror are less than 1,000 atoms thick. As for the telescope's abilities, it would be able to clearly see a US penny from 24 miles away and a football from 340 miles away. James Webb's telescope side is cooling itself down, and its temperature doesn't rise higher than minus 370 degrees Fahrenheit. That's cool enough to make liquid nitrogen. A truly enormous 5-layered sun shield surrounds the telescope and reflects away as much sunlight as possible, letting the telescope stay cool. Attention! Attention! Emergency alert! This is not a drill. The Milky Way is on fire! I repeat, the Milky Way is on fire! Evacuation protocols activated. All terrestrial life forms are to be moved to the Andromeda galaxy immediately. I repeat! Wait, a fire in our home galaxy? It all comes down to the incredibly hot gas surrounding the Milky Way. This isn't just intensely hot, it's also existed for billions of years. But what's heating this gas and keeping it that way? The Milky Way holds far more gas than stars, and this gas is crucial for forming new stars. Over billions of years, this massive reservoir has allowed the galaxy to keep producing stars. But this gas is incredibly thin and spread out, which makes it next to impossible to observe it directly. For a long time, this made it difficult to figure out how much gas the Milky Way really contains. But in recent decades, researchers finally confirmed that the galaxy is indeed surrounded by an enormous sphere of hot gas. This gas cloud extends as far as 700,000 light-years from the galaxy's center and reaches temperatures of several million degrees. At first, scientists thought the gas's insane temperature was due to the Milky Way's gravity. They believed that gravity caused the gas to swirl around, keeping it from falling inward and heating it up in the process. But then, recently, scientists have discovered something even more surprising: a second layer of gas. And it's even hotter. How did we discover this gas with a temperature of around 18 million degrees Fahrenheit? Faint X-rays coming from all directions in the sky revealed the presence of this gas. The gas also showed up as it absorbed light from distant quasars, bright objects far outside of our galaxy. No wonder scientists began looking for the sources of heat that could explain this bizarre phenomenon. They soon found that the two types of gas, the X-ray emitting gas and the absorbing gas, came from different regions in the galaxy. The X-ray emitting gas is apparently produced by a puffed-up region around the Milky Way's stellar disk. This region is a direct result of the galaxy's star formation, which is still going on. Massive stars in these regions eventually explode as supernovae, releasing huge amounts of energy. This energy heats the surrounding gas to extreme temperatures. The gas heated by supernovae becomes turbulent, moving around chaotically. Some of it escapes into the space around the galaxy, while some of it cools down and falls back toward the disk. This continuous cycle of heating, cooling, and movement keeps the hot gas layer visible in X-rays. The absorbing gas is enriched with elements like sulfur, magnesium, and neon. These elements are created inside massive stars through nuclear reactions and escape into space during supernovae explosions. Runaway stars that are flung out of the Milky Way's disk also contribute to this process. When they explode as supernovae, they create pockets of enriched gas above the galaxy's disk. The X-ray emitting gas forms a glowing layer around the Milky Way's disk. This layer never disappears due to the star formation and supernova activity happening in the galaxy. Together, these processes explain both the absorbing and emitting signals observed by astronomers. Star formation, supernova explosions, and gas movement all work together to shape the Milky Way. The hot gas not only helps regulate star formation, but also redistributes materials created inside stars. And elements produced in stellar cores are spread throughout the galaxy by supernovae, becoming the building blocks for future generations of stars. The research team plans to keep observing the gas at other wavelengths of light. This might give us even more information about how the gas behaves and what it's made of. And once we understand the dynamics of this gas, we're likely to learn more about how galaxies like the Milky Way evolve over time. We need all the data we can collect after all. We don't even know the true shape of our galaxy yet. Recent discoveries have revealed that the Milky Way is not a flat disk as previously thought. No, it has a warped structure. And the craziest thing? Dark matter might be the cause of this deformation. The first confirmation that the Milky Way isn't a perfectly flat disk came from observations by the Gaia spacecraft. Gaia mapped the positions and movements of over 1 billion stars, and its observations showed that the Milky Way extends farther outward than initially believed. At its edges, the galactic disk was a wavy, warped structure with serious deformations along the outer edge. But what causes the warp? These deformations may result from ancient galactic collisions, like the Milky Way's collision with the Sagittarius dwarf galaxy around 6 billion years ago. However, a new study suggests another possibility. The warp might be caused by a tilted dark matter halo surrounding our galaxy. Dark matter halos are invisible, yet massive structures surrounding most galaxies, including the Milky Way. These halos contain most of a galaxy's mass and have a strong gravitational influence on the galaxy's structure. If a dark matter halo is tilted relative to a galaxy's plane, its gravitational effects could distort the galaxy over time. To figure out whether this theory is true, researchers used data from highly detailed computer simulations that modeled galactic evolution, seasoning the process with dark matter and interactions between matter and magnetic fields. The analysis revealed that the inner region of a dark matter halo can indeed tilt significantly with respect to a galaxy's plane. This tilt could result from galactic collisions or close encounters with other galaxies. Such crooked halos can stay this way for billions of years, which is long enough to warp the galactic disk. At the same time, this phenomenon isn't something unique. Astronomers have observed warped planes in other galaxies as well. In fact, nearly half of all spiral galaxies in the universe have warped disks. So, tilted dark matter halos and their gravitational effects might play a widespread role in shaping galaxies over time. While we're looking for answers, the Milky Way continues to shine brightly. But what kind of space electricity keeps its lights on? What fuels the process of star formation? After all, roughly one sun-sized star is born each year in the galaxy, and it needs a lot of fuel. Star formation requires hydrogen, the most abundant element in the universe. But it would still have been depleted long ago, unless there were a replenishing source. The source might be fast-moving hydrogen clouds raining down into the galaxy's disk. The hydrogen fueling the Milky Way is ionized, making it challenging to detect. Unlike atomic hydrogen, which emits light, ionized hydrogen does not. Instead, it absorbs light, which means it can only be observed when it passes in front of a bright background source. Before, astronomers used quasars, extremely bright distant space objects, as backlighting to detect these gas clouds. Unfortunately, in this case, it was impossible to determine how far away the clouds were. They could have been located anywhere between the Milky Way and the quasars billions of light years away. To pinpoint the location of the gas clouds, astronomers turned to the cosmic origin spectrograph aboard the Hubble Space Telescope. They observed 27 stars located within 10,000 light-years of the Milky Way's disk. They analyzed the stars' light and found that about half of the stars were obscured by gas clouds. It means they were close enough to directly feed the Milky Way's disk. The researchers calculated that the gas clouds contained a total mass equivalent to a whopping 110 million suns. This vast reservoir of hydrogen offers more than enough fuel to sustain the Milky Way's star formation. But where did those clouds come from? So far, it still remains a mystery. There are two main possibilities. The cloud might consist of hydrogen formed shortly after the Big Bang, primordial gas. These structures could have remained outside any galaxy for billions of years, only recently falling into the Milky Way's gravitational pull. Or the clouds might be made of material ejected from the Milky Way itself. When stars explode as supernovae, they can blow gas outward. Over time, this material could cool and fall back toward the disk, forming the clouds. We'll be able to figure out the origin of the clouds only after studying their chemical makeup. Gas from exploding stars contain heavier elements, while primordial gas created after the Big Bang is composed almost entirely of hydrogen and helium. Future ultraviolet telescopes could provide the detailed measurements needed to settle the question.